Okay, thank you very much. The first question is, can you guys hear me all right? Because I can hear a lot of noise when you speak. So you guys can hear me well? Hello?
Yes, we can hear you well.
Okay, so there is no noise on my side.
No.
Oh, okay. So first of all, I'd like to thank the organizers for this opportunity. And I'm really sorry I cannot be in Vienna because that was my wish. And unfortunately, I had to cancel my trip. But I'm glad I'm able to deliver this lecture anyway. And so again, thanks for the opportunity of letting me explain my research. First of all, there are the three logos of my three European projects. And before I start, I'd like to just advertise the Cost Action Calista, which I lead. And there is one working group, which is absolutely in line with the themes of this workshop, which is called Vision and Machine Learning. And I wish everyone to join this cost action, cooperation and science and technology, and it costs nothing and only money can come your way. So there is really no reason why not joining it. And I wish you all guys will send me an email, Rita Fioresi, and ask me how to do it, because this is really a wonderful opportunity, especially for younger people. Okay, so this is the plan of my talk. So I will give a very brief introduction to deep learning and geometric deep learning, because my research is geometric, but very much motivated from the functioning of these two algorithms. Then I will say a few words on information geometry, and this was already introduced yesterday and the day before, so I'll be really fast, and I'm glad that such wonderful talks occurred yesterday, so that I really have very little to say. You already said everything that was needed for the background. In particular, about the Fisher matrix, this is the Fisher-Rao metric that they were clearly explained yesterday. But I also wish to introduce something called the data information matrix, which is a new concept that me and my co-author were investigating. This data information matrix is leading to concept of foliation in the data space in deep learning. And also, as last part of my talk, I like to speak about some physical modeling of the deep learning and geometric deep learning algorithm. And all of this research is joint work with my student, PhD student Elio Tron in Toulouse, and my PhD student Michela La Penna in Bologna, and my co-author Faglioni. Okay, so for each of these topics, I put references, and for the deep learning and the geometric deep learning, it's impossible to make a comprehensive reference. So I send you to my paper with Zanchetta, my collaborator, where we do some introduction to these algorithms dedicated to mathematicians and physicists, and we put a long list of references, and so you can read there what this algorithm is about, okay? So I'm not putting myself a reference, I'm putting all the references into my paper, because it's impossible really to give a credit to who invented and who first studied this algorithm. Certainly, Jeffrey Hinton and Jan LeCun are recognized initiator of this research, and Michael Bronstein for deep learning, while Michael Bronstein for geometric deep learning. But again, this is a very reductive point of view. Okay, so let me do like a one slide introduction to this algorithm, because I will need some minimal background to explain the geometric concept. So what is deep learning? Deep learning are what are known as convolutional neural networks. What does this mean? It means that you have an image that is explained here just by giving you this very stupid picture, because an image obviously doesn't have a 16 pixel, but have many more pixels, evidently. And the way this algorithm is processing the image, so you give different images corresponding to certain number of classes. For example, you have 10 classes, which are the 10 digits between 0 and 9. And then the purpose of the algorithm is to recognize whether or not a certain image belongs to a class. So you give an image of a certain number, say the digit 1, and the algorithm is supposed to recognize if it is a 1, 2, whatever it is, okay? This is how it is achieved. There is something called convolution, that you certainly know what that is. You are sliding a certain pattern that here is represented by this square along your image, and then you're doing the multiplication pixel-wise. Why is this done? Because in this algorithm, there are these many matrices that you slide, and you're trying to learn features. So you're trying to learn direction, curvature, and so on. I will become more specific later, but I'm trying to tell you that this is like a recipe extracting features by learning them from images. And then once the algorithm is trained, you use them to recognize every image. Now, the geometric deep learning algorithm exploits somehow the same idea, except that instead of looking at convolutions on an image, which is essentially a grid distributed information, you're looking at a graph convolution, making the whole idea more complicated, because it is clear that while you can slide a matrix, you know, along another matrix, so really it is the same idea as Fourier, you know, with a kernel you transform. With the convolution, with a graph, the convolution is more complicated from the fact that every neighborhood is different from another one. So, for example, this red dot neighborhood has 4 edges. This one has only 2 edges. So how can you do a convolution? So this becomes a much harder problem and can be solved, of course, in different ways. Okay. So let me briefly tell you the main ingredient for the deep learning algorithm, and then also for the geometric deep learning algorithm, because in this talk I will speak about both. So there is something called a score function. So what happens is that you are giving me some data. So you're giving this data X, and X can be an image, for example, and you're giving me some weights. These weights are originally given randomly, and then you compute a score. For example, for this F is my score, is just a matrix multiplication. Okay, this is a linear classifier. Convolutions are a bit more complicated, but the idea is exactly the same. Then you measure the error that your prediction is giving. So this W are your weights. You produce from the score some probability that you see right here. So you do the exponential of some score, and you divide by all the sum of the exponential of the others, because this is clearly a vector, this F, and this gives you a probability. So for example, if you have 10 possible classes, this F will be a 10-dimensional vector. It will have some entries, and then you do this function here called the softmax function, and this transforms your vector into a vector of probability. In other words, they add to 1. It is a very simple way to do this. It's not very smart, this idea. It's just how to transform a generic vector with 10 entries into a vector that has positive entries, and they all add to 1. And then this loss function, L, will measure the error committed by your algorithm. So your algorithm will give a certain probability that your image is one of the classes, and the loss function will tell you whether or not this prediction is correct and how far is from the correct prediction. We're going to come back to this very important concept later on. So don't worry if you don't get it, because we come back to it. And also yesterday, there was some argument about the information loss, how this was studied, and this is exactly that one, okay? So, but we will come back to it. So I just wanted to give the essential bricks to build this algorithm. So you score, so you give a score to every image, then you tell me whether or not the prediction is correct, and then you need the optimizer. What is this optimizer? You want to try to move your weights. So remember, the weights are given randomly at the beginning. So clearly, if you give random weights, the prediction is going to be very wrong at the first run, obviously, because it's random. Now, the optimizer will move the loss, the parameters W in such a way that the loss is minimized. I'm putting the quotation marks because we are moving along the gradient of the function. So you see here that we take the gradient of the loss function. Hence, you're moving in direction opposite of the gradient. It means that locally you're going towards a direction that is decreasing the loss, okay? However, there is no guarantee that if you take this step at each, you take a movement towards this minus the gradient, there is no guarantee that you reach a minimum, not at all, because only if the function is convex, otherwise God knows where you're going. To complicate matters, you are not taking all the loss functions, so you are not measuring the error that you commit on your training images, but you're taking only a portion of the loss function. And this portion is here, in this example, obtained by summing only 32 images data, if you like, making the calculation very noisy, because depending on which 32 images chosen randomly you are computing, obviously you get a different direction of movement. Okay, so this is the three main ingredients. I promised that I would pause like every 5 minutes. Everything so far, you guys are hearing me correctly? Are there any questions about these main ingredients?
Okay, seems to be okay for now. Thank you.
Okay, no, I'm just pausing to make sure we are all there, and it just, online talks are a bit tricky.
Thank you.
Okay, so what is the training of a neural network? So you take your data, for example, the cipher 10, but this is also the missed digit, whatever data set you have available, and you divide your data in 80%. This is, again, a percentage that I'm making up. There is no, say, what if I want to do 75? That's okay. So you take the major portion for the training, then 10% something called the validation, and then 10% just for the test. Okay, let me check if you guys are still here, because you are here. Sorry, because here something strange happened. Okay, thank you. Okay, fantastic. So we start the training. The training is the learning phase where we determine the weights. How does it work? It works like this. We run the algorithm. Essentially, we compute the score in some way. We compute the loss, on which I will comment later. And then we move towards the minus the gradient of the loss. And we do it many, many times. So at each step, we're moving to the negative of the gradient, so towards a minimum, hopefully. Okay, so we do this training phase where the algorithm sees many times the images, and in this process we hopefully reduce the value of the loss. Then once we have learned the parameters, the W's, we do a validation. What is the validation? We decide perhaps to change some structure of our network. Perhaps we add a layer, we change what is called the learning rate. So we're a bit changing the structure of the algorithm to see whether or not we can improve our performance. Now, once we have decided with the 10% of the data that we're very happy, we test on the 10% of the data, and we do it only once. And the accuracy is corresponding to the percentage of accurate prediction on total predictions on the test set. I'm putting down here this very strange image. Oh, that's the problem. Sorry, I'm in a room where things are misbehaving. Okay, I'm trying to make things function. Okay, my students are saying they can follow. So there is something called the loss landscape, which is like a projection of the loss in 3 dimensions. And I think it's pretty clear that this loss is a very rugged surface, and essentially the stochastic descent, the gradient descent, will move in this landscape. There is in this picture a minimum, but you never want to get this very low point of the loss, because this point will correspond to something called overfitting, meaning that you are adapting your net totally to your data set. Hence, it is not able to properly learn the features, but it's just adapting. So it's like you are assigning a weight to say that it's like you're assigning to your training set the correct label. You're not really doing a full learning procedure. So here you don't want to go. Okay, I want now to go and speak more about geometry. But before I do this, are there any questions on this very, very fast crash course on deep learning I gave? So far, so good. Very quick course.
It still seems to be all good. Thank you.
Okay, great. Now we're going to talk a bit more about geometry. So the references are Amari, which has been already quoted, cited in this workshop. Nielsen, also cited, but I would like to add also Martens, because I learned a lot in reading his notes. Okay. Okay, information geometry. So it studies the geometric structure of manifolds in the parameter space. So essentially, if you look at the parameters of a deep learning algorithm, they will give you a probability, right? So in some sense, this space of parameters in the deep learning algorithm is the space of probability distributions. And this is something that, like with the concept of varifolds, we already encountered in this workshop, but it's very fun to hear. But in this case, it's really like empirically giving you this. And there is something called the information loss, which is minus the logarithm of probability. And this was already introduced on Monday. And essentially, what this information loss is telling you this, okay, it's just minus the logarithm, but there has been some interpretation on how this is obtained. And that is something. Actually, here there's an expectation value missing. Okay, I'll come back to the information later on. And there is something called the empirical loss, which is really what is used as loss function, even though we don't see it really immediately. Okay, I will add a slide explaining it. So let me show in this picture really what this is about. So suppose that we have samples and we have cat, horse, and dog images. Then we throw them inside the algorithm. That here is just a multi-layer perceptron. It doesn't matter what it is, not at all. But this algorithm will give you, for each image, you see 3 numbers, is the score. So you give the image of cat, and the score for cat is 5, the horse is 4, dog is 2. So that's okay. That is a nice idea because it's nice prediction because it's actually predicting better the cat. And then you do the softmax function, which is explained here down below. So you take e to the score 5 divided by the sum of the scores. And this clearly gives you the probability that is catching the correct class, 0.71, okay? So not so bad, right? But it's giving you also other probabilities. So if you were doing the softmax, you see for so this is one probability, but you can do probability for horse and dog, and this will give you, of course, it sums to 1, though it doesn't look like it sums to 1 because there is some computational error. For example, this probability can never be 0 because it's an exponential, but okay. So we get the idea, right? So here we have 3 labels, and we have the 3 probabilities. Now, the empirical loss function is actually related to the Kullback-Leibler divergence. We discussed this, I think it was yesterday, okay, and is very interesting this because so you are computing the expected value of your information minus logarithm of p with respect to a mass probability distribution Q. So Q will be 1 whenever you have the right class, 0 otherwise. So Q is the true probability distribution. And if you make a little calculation, it's very like immediate calculation. You see that this is the Kullback-Leibler divergence, as was introduced yesterday, measuring the difference between 2 probabilities, and then this expected value of the information, okay? Now, when Q is a mass probability distribution, this term is 0. Why is it 0? Because it will be when Q is equal to 1, when logarithm of 1 is 0, okay. When Q is not equal to 1, you have 0 times the logarithm of 0, which I know mathematically it doesn't make sense, but come on, we know that is 0, right? That's essentially the bottom line of this, especially because in the computer, nothing is truly 0. So this should be not really equal. Okay. Are we happy with this very fast introduction of Kullback-Leibler divergence, the empirical loss function, which is, by the way, is called the cross-entropy loss. That's another way, is measuring entropy of one probability with respect to the other. But we spoke already about this in the past 2 days, so I was very fast on it. Are we happy? Yes. Okay. Thanks a lot. Okay. Now I want to come to the heart of my talk and talking about the Fisher-Rao matrix and the data information matrix. So the references are my work with Crementieri, that was my master's student, work by Tron, and this new preprint that I have with Elliot. That is the 3 references. Okay. So we already saw during this workshop that we can introduce the Fisher matrix, and this is the expected value of the gradient with respect to the parameters that describe my probability. And that I don't comment because we discussed this already in this workshop. And then there is something called the data information matrix, which is a bit less known, but it is really the same idea, except that instead of taking gradient with respect to the parameters, you take gradient with respect to the data. Now, it seems a bit weird because you think, oh, wait a moment, the data is like given to you. So how can you take a gradient? Because the data doesn't vary, it's just that one. True, but you may think the data as inside some big space, and so you can move around in this space. We have a key fact that was mentioned, I think, yesterday, that the Kullback-Leibler divergence that measures the distance between two probability measures is a very effective way to introduce a metric in the space of probability distribution. In fact, the Fisher matrix tells me somehow you see, it is an effective scalar product in this space. I mean, we discussed this. I saw it online that there was this discussion. I mean, this equation tells it all, right? That Kullback-Leibler measuring the distance is approximated by the scalar product obtained through the Fisher matrix. Actually, you may say the same for the G, the data matrix, which I call also the DIM. Now, it is very interesting because this distance in the data space is actually answering to the question, if I move a little bit in the data space, do I obtain something that is the same like type of data or not? Because if I move really far, it is evident that if I start from the digit 0 and I move far from the digit 0, I can hit in the data space any other digit. However, if I move a little bit, of course, I will stay in something that is very similar, okay? It is, however, very important to realize that if you're computing the probabilities of the deep learning algorithm, while you are training the algorithm, you get certain meaning of them. If you're letting the training to reach the end, when the probabilities are certain, this Fisher and this data matrix lose their significance. I try to write here a little picture because I think this picture is very telling. It's showing the trace of, these are definite, semi-definite positive matrices, while there is the training. As you can see, we start from 0.7 and we go to 0.02. So it drops really, the eigenvalues will decrease in their magnitude. Meaning that if you push the algorithm to the end of the training, you cannot get a meaningful experimental information through these matrices. Because for me, there is the mathematics, which is great, but there is also the empiric evidence. And if the mathematics and empiric evidence do not match, to me, means that we need the new mathematics. That's the way I see this. Okay, so let me tell you the facts that we discovered about the Fisher and the data information matrix. Very simple to show their positive semi-definite symmetric matrices. Now, we calculated the kernel in the case of a deep learning ReLU neural network. So this probability, remember, they are computed through the score. So it is very possible mathematically to compute this matrix and to look, I mean, it is ugly, we agree, very ugly, but we were able to prove that the rank of the Fisher is bounded by the number of classes, okay? Now, let us see, and similarly, the rank of the data matrix. They're both bounded by the number of classes. Now, this means that a matrix for the mixed data set, which are the digits, that is of size 784, so this is a square matrix, 784 times 784, it has a rank 10, okay? Meaning that is very far from being invertible, and it has a very low rank, okay? For the Schiffer and ImageNet is even more dramatic, this bound on the rank. So one may think at this point, then it is not a metric, because you're trying to give a metric on the probability space, and you have a very degenerate. However, the situation is not as bad as it looks. Okay, so you can look at two distributions. So if you are a mathematician, you know that whenever you have available some nice vectors are the gradient of the probability, logarithm of the probability, you can compute distributions. Distributions are subset of the tangent space. In this case, the situation is very simple because we are in Euclidean space. So we look at the image of the data matrix, and if you substitute the Fisher, it is really the same. The image is spanned by 10 vectors, actually 9, because probability, of course, there is a relation, so 9 vectors. And these are the gradients of the logarithm of probability. And then you can look at the orthogonal distribution, which is the kernel, and this is, of course, the orthogonal. And you can hope, and I will see how much hope you can have, this subset of the tangent space actually correspond to foliation, meaning that there are some sheets of paper that are called leaves that are tangent to these distributions, okay? So we're trying to determine some structure into the set of data. Oops, sorry. And now I'm going to the foliation. Okay, so I'm trying to move this, see if I can, but perhaps I cannot because it's disturbing my talk. All right. So the data occupies a little portion of Rn, evidently, because if you look at data, it will be, if you just pick a point in R784, it's going to be noise if you choose randomly. And I have this nice picture, so you can see this yellow sheet of paper, which we call the data leaf. Even if with my student, Elliot, we discovered that is a bit improper. We should say data leaves, more than one, but that's okay for now. On the data leaf, so there is this little manifold that has dimension 9 sitting into this very big space. And the meaningful data, these are the digits, sit on this sheet of the space. So with Grementieri, we proved that the data domain, it decomposes the disjoint union of submanifold, and that's a theorem. Okay, and this dimension of the leaves is bounded by the number of classes. What you cannot prove with the theorem is the fact that the data indeed is on one of these leaves. You cannot, because data is just a point, right? So what we did with Grementieri, we gave some experimental evidence that the data, you can move on a leaf and you see meaningful data, okay? If you move away from the leaf, you are adding noise. That we could do experimentally. Let me show you the mathematical result. So if we take the weights of a deep ReLU neural network classifier, so essentially a deep learning algorithm, with the probability given by the softmax, and you take the data information matrix, then the distribution on an open set of the data domain is involutive. What does it mean? That if you take the Lie bracket of two gradients of the probability, you stay in the distribution, okay? This fact is non-obvious at all. Why should that be? But we proved it. It is true. Now, this is really great because every time that you find an involutive distribution, Frobenius theorem tells you that you have a foliation. A foliation is exactly what I described above. Your data space will divide into a disjoint union of manifolds. And to each leaf, each manifold, you will have a non-degenerate data matrix defining its tangent space. So the data matrix restricted to each submanifold is giving a meaningful metric, a non-degenerate positive definite metric. This is a great news. However, If you try to repeat this calculation for the Fisher, you see immediately that though they look very much the same, the difference is too great. So the Fisher matrix is not involutive. Actually, if you take the bracket of two probabilities with the Fisher matrix, you essentially get a bracket generating property. You get outside the span of the probabilities and you generate the whole space. And this is, I don't want to say it's bad news, because for me it's exciting news, because it tells me that there is some sub-Riemannian dynamics that one has to understand properly, but we have not done this study. Okay, so we concentrated on the data. Okay. So what are the facts that I just summarized? So the matrix G, when restricted to a proper subspace of Euclidean space, give a Riemannian metric. Actually, looking closely to it, unfortunately, it's not a constant rank. So is it a metric? Again, is in the realm of sub-Riemannian metric. And it is something called singular foliation theory that is very exciting in mathematics nowadays. It requires the machinery of Lie algebroids, and we are working on it to understand properly. And of course, it's non-smooth. So there are some points that you have to ignore. What we proved with my student is that it is smooth on an open set. So we prove that it is a measure zero, the set where it misbehaves, at least good news. The fact that one leaf, or perhaps more than one leaf, contains data points tells me that we perform dimensionality reduction. So we are able to characterize a portion of the data space where the data, the meaningful data, are contained. In particular, I want to put the extra difficulty that I want to put your attention that the data is contained in a cube, because the digits are not allowed to take any value. So there is the pixels are between 0 and 1. So this gives you extra problem. Okay, but this is a technical problem. So far, so good. Are there questions? Because I want to say something more about the foliation structure.
Seems to be still good. Thank you.
Okay. So I just wanted to tell you that some of the deep learning algorithms will have the GELU, so-called, that is not as the ReLU. So the ReLU will produce, here you can see, some score, to show you that there are many angles where the data space, of course, this is a very, what can I say, it's not a true image, because in the MNIST it's impossible. So we are looking at XOR, so it is only two classes, but okay. Just to tell you that you can get a smooth distribution if instead of non-linearity as ReLU, you take the GELU. For those of you that know what it is, for those of you that don't, that's okay. I'm saying that instead of ReLU, you can smooth your distribution. However, if you decide to smooth your distribution, you lose involutivity. Okay, so really the ReLU, which is the most popular, is involutive, the distribution, but the moment you go away from the ReLU, you lose this feature. And so essentially, you don't have a foliation because Frobenius theorem. I just wanted to give you a feeling of what happens when you go in a direction perpendicular to a leaf, okay? So if you go away from a data leaf, so you take the number 0, and then you go orthogonally. So as you can see, the label is 0. The algorithm is predicting label 0 with high probability, and you are seeing a lot of noise, very unpleasant. So this same thing for the number 2. look, this is predicted with probability 0.92, and it is basically random noise, okay? So what I'm trying to say is that this can be used for the so-called adversarial attacks, where you try to trick your network into a false prediction on some data set. This is work by Tron Quelan that I don't quote here, but it's been the object of research. There is also a possibility of knowledge transfer. What do I mean? Knowledge transfer is very hot at the moment. Of course, we're doing proof of concept, and we look at the singular value of the matrix of, you know, is not exactly the data matrix, almost the data matrix. You see that on data points, the data matrix has a very diverse eigenvalues. On random points and noise points, the eigenvalues are practically very similar. And so this magnitude of eigenvalues can be used to measure the distance between data sets. So if we take 6 different data sets, you can ask yourself, what is the distance? And you see, the magnitude of the eigenvalues can somehow give you some answer. For example, it is clear that the red is the, you know, the noise. The noise is different from everything, obviously, because it's noise. The others, some are closer. So, for example, this picture tells you that some data sets are closer than others. So the CIFAR, for example, is the orange. It looks far away from the blue, which is the mist. And in fact, it's true because the mist are digits, the CIFAR are other images, so somehow captures a little bit. And why do we use it? Because then we try to estimate how expensive it is to retrain your algorithm based on the distance with the previous. And we see that the loss function for the CIFAR is worse, behaving worse. And also the accuracy is much worse than the others. So what we're trying to show is that when you are close to your data set, so for example, if instead of digits you take letters, then it's close and it retrains easily. If you take images like in CIFAR, then it's very bad. But so this is a proof of concept that we are trying to push. And then also we went into the direction of explainability, because we try to look at the distribution restricted to our, you know, the tangent space to the data manifold, the data leaf, right? So if you look at this 10 by 10 matrix, for example, we look what happens in the point 2. We see that the only 2 probabilities that are non-zero are 2 and 4. And if you look at the 2, it looks like a 4. No, but it looks more like a 4 than like a 2. So notice that here we're not determining the probability of the number 4. We're looking at the gradient of the probability in the direction 4. Similarly, for this other number 2, well, this number 2 now shows 8. Well, yes, because it's still a number 2, but it looks more like an 8 to us, right? So I'm trying to tell you that this dim will somehow tell us, yes, the probability is 2. Greater is 0.95 is a 2. But if it's not a 2, it could be an 8. And in fact, not in probability, right in the gradient. So it's, I mean, similarly for the number 9, see, it highlights the number 0 because it looks like a 0, right? Somehow it's the, okay, so we like this explainability. Okay, so I want to conclude. Then I had some observation on geometric deep learning, but perhaps I don't have the time. So let me draw the conclusions. So if we use a partially trained model, so we cannot push the training to the end because that will destroy the eigenvalues of the matrices, we can construct a low-dimensional submanifolds that we call data leaves, which are totally related with the data, meaning that if we move around on these data leaves, we see meaningful data. Okay, so this is, and if we move orthogonally to these data leaves, we are adding noise. Though we are adding noise, the model will not change the accuracy, so it's through adversarial attack. What are the possible applications? We are looking at the denoising of images, the knowledge transfer, and also to explain how the algorithm reasons looking at this image. Now, what are the future directions? We want to understand the geometry and metric structure of data leaves. So I was hearing the very suggestive talk by Le Brigand, talking about these alpha connections. Of course, we computed the connection with respect to the data matrix, but perhaps that's not the right way to look at it. Perhaps it is necessary to go beyond the Levi-Civita of this metric and look at the alpha connections. That I think is a very nice, analogy. I mean, sharing my research, teams of research. We need to go to the proto-Sub-Riemannian geometry, Lie algebroid language for sure, because the problem is that this metric is severely degenerate. And we need to go to the language of singular foundations. We have to understand the geodesics. So what are the geodesics in this, and how to navigate the data leaves? Because this could lead to data augmentation, it could lead to knowledge transfer and many more applications. So I promised I was going to finish 10 minutes in advance. I have the thermodynamic part of my talk, but I guess that I'll be done for now. Thank you very much.
Thank you very much. Other questions or comments? Yes, so the microphone is there, so if you can maybe.
I'm not sure. Can you hear me?
Yes.
Hello, thank you for the talk. I'm not sure if I understood correctly how exactly you're using the data information metrics. Do you use it somehow during training, or is it just an evaluation technique for adversarial attacks?
Okay, thank you so much for the question. I was very fast indeed. So the way we do it is that we train our model, okay, and but we do not push the training to the end. And once the model is trained, that we have the W, okay, so we fix the parameters W, we compute the data information matrix, okay? So it is not computed during training. You could compute it during training, but we don't. We compute it at the end of the training, right before the end. Fixing the parameters and computing the gradients with respect to little changes into the data space. Is it clear?
Yes, thank you.
Okay.
Barbara, that was a question.
Yeah, can you say something about the thermodynamics that you have at the end? Can you say something about it?
Can you speak a little slower because the sound is not perfect? Yes.
You have some slides about thermodynamics, right? At the end, can you
True. Yes.
share with us?
Okay, very fast. 2 minutes about thermodynamics. So there is this stochastic differential equation through the Ito formalism that is modeling the stochastic gradient descent. Okay, so here, this is the stochastic updates of the weights, where we don't take the full loss, but we take just mini batches, and eta is the learning rate. And this is modeled through this stochastic differential equation, where you hide the stochasticity into this term. So W is the like Brownian motion, and D is what is called the diffusion matrix that control the anisotropy. Okay. Now, in the paper by Chaudhary and Soato, they computed the notion of temperature, capturing the amounts of noise during the stochastic gradient descent. Now, what we did with my collaborators, we give another notion of temperature that is linked with the kinetic energy, which is the velocity squared of the parameters. So that, of course, you have to compute it while you train. Is necessary because otherwise you don't see the velocity. And the delta t here, you set it equal to 1, similarly to the mass of the parameters. And then you can take this time average of the temperature, you compute it, and you ask yourself how hot is a filter of your geometric deep learning and how cold. And what we discover is that if you kill hot filters in deep learning, the accuracy doesn't change. You see, your original model is 98.80, and this one is 98.5. So it's really no change. While if you kill the coldest, so you set to 0 all the parameters of the coldest, you see immediately that you get a very low accuracy. Okay, so this drops accuracy. So the bottom line is that if the parameters of a filter are very agitated, it means that that filter is not capturing any feature. So if you remove it, it won't make a difference. While if it's a filter is cold, so it doesn't move anymore, so it is stopping, then is somehow a meaningful filter because it's captured the correct feature. I think I will stop here because then there will be some geometric deep learning and I really don't have the time for that.